So for the second portion of our class on macromolecular instrumentation, we'll be looking at using robotics for drop setting, for setting up crystallization experiments, and also imaging to image your crystals in your experiments as they progress. Okay, there's a lot of benefits and value when we use robotics for crystallization, both experimental setup and imaging. On the sample setup side, there's always speed. There's also consistency, the ability to use very small volumes. When we set by hand, typically drops are 1 microliter. With the robot, we can use down to 100 nanoliters. There's also reduction in human error, and the precision and volume is far better. And then when it comes to imaging, again, speed, and the automatic imager will generate far more data than any manual inspection could. It keeps detailed records that you can go back to. Again, there's a reduction in human error of identifying crystals and precipitant and things. You're able to take data in a time course manner. The software also has a very good auto-scoring system, which we'll talk about. There's also no temperature variation or possible mishap. The crystallization tray doesn't have to leave the incubator to go to the microscope. We're able to take high-resolution images right away, and we also can use UV tryptophan fluorescence to try to identify whether crystals are protein or salt. This is our TTP LabTech Mosquito drop setting robot. So in the earlier portion of the class, you've observed setting up crystal drops by hand. Here we're going to demonstrate a robot that can set up the drops robotically, which is both quicker, more efficient, and more precise. So the way this works is that it uses these individual tips, and within the head here is a mechanism that acts as a multi-channel pipetter. So the individual tips are here, and it picks up 8 tips at a time, and those function like small volumetric pipettes, and they can hold up to 1.2 microliters each. Now we change the tips in between solutions for cross-contamination to prevent it. And we have a spool of extra tips here. There's about 20,000 tips on here, so this will last a while. And the basic experimental setup is as follows. We have a special tray here that we put a few microliters of our protein in each one of these wells, and each well takes care of a row. Then we have our tray cover here, which is set up with spaces in between the glue, and that's where the drops are going to go. And finally, right now it's underneath the head. If I move that over, that's our crystallization tray that currently has 100 microliters of well solution in each one. So once you've set up the physical part of the experiment, we go on the computer, and in the software, we set it up. We tell it what type of plate it is, so it knows the definition. We tell it the volumes we want to use. In this case, we're doing a 250 nanoliter protein and 250 nanoliter of precipitant drop. Okay, once you have your experiment set up on the deck and the software is ready, then we're able to press play and start the experiment. So at this point, the robot is initializing its motors. It's grabbing a fresh set of tips. Now it goes down. The first thing it does is it picks up some protein, and it's going to aliquot the protein 250 nanoliters at a time in each space. So at that point, we can see the 250 nanoliter drops. It's going back to get more protein. Our second set of 4 columns is set. And there's our third set of of protein columns. It exchanged to have new pipette tips to avoid cross-contamination. And what it's doing now is it's pipetting 250 nanoliters of each column of our well solutions onto the top of the drops. Now you'll notice it's going from column, starting on the left side of the tray and ending up on the right side of the lid. That's because, since this is a hanging drop experiment, at the end we'll flip over the lid and put it onto the tray, so we have to set it up in a mirror image. So as it's going along, you'll see it's adding 250 nanoliters of precipitant to each drop, and it's also exchanging the tips each time to prevent cross-contamination between the different well solutions in the screen. So we'll just let it finish up. Okay, so the robot has finished the program, and we can see here we have our 96 drops set, 250 nanoliters plus 250 nanoliters. So what we'll do now is we'll put the cover onto the tray, and we'll do that using this jig here. So if you remember, this is a hanging drop experiment, and it was set up in a mirror fashion. So by using this jig, I can take the plate, line it up into the jig like so, and then simply take the block, and I'm using a little bit of 50% ethanol in between the cover slip and the block for some surface tension. Just flip that over, and it fits right in there if you line it up to the three guide poles. When you put it down, it's in the right spot. Slide the block away, and that leaves your lid in place. And there we have it. We have our completed tray. We can use this brayer to seal the tray, and our hanging drop experiment is done. At this point, I already have a barcode set up for the imager, and we'll get to the barcodes and the imagers in a later portion. So this is the Formulatrix NT8 drop setter. This is a second example of a robotic drop setter that allows us to set up crystallization experiments. The basic operation is similar to the Mosquito. There's some subtle differences. Rather than using a spool of tips, it uses these individual pipette tips here for the low volume handling, and washes them in between each step. And that will use less drops, or less tips. There's an advantage to this machine where it will start with a deep well block of a screen and use large volumes to copy that block to your experimental tray, and then set up your hanging drop experiment. So in this case, we'll set up our protein in the protein well. This is similar to the Mosquito, where each drop sets up a row. We have our crystallization lid in place and our crystal tray. So then we'll go to the software, and we can see the software knows about our deep well block and our set of high volume tips and the low volume tips, and has our crystallization lid and tray. Then in the procedure, first thing we're doing is copying 100 microliters of the deep well block to the crystallization tray, and then we're setting up a hanging drop, again in a mirror fashion, which is a 250 nanoliter protein, 250 nanoliter crystallization solution drop. Okay, so once we're ready, and the protein and everything's set up on the deck, start the program. So the multi-channel header head is coming down. First thing it's doing is it's going to copy the deep well block 100 microliters at a time to our crystallization tray. And it'll continue that for the 12 columns. So we'll let that go. So the NT8 is finishing up the plate copy from the deep well block to the experimental plate. So it's done with that portion of the setup. So what it'll do now is switch from the high volume multi-channel head to the low volume multi-channel head, pick up a set of the low volume tips, wash them first, just pushes water through the top of the tip down to the bottom of the tip. Picks up 250 nanoliters of protein, and it's going to go to the well, pick up 250 nanoliters of the well solution, and dispense both of those in column 12. Now, again, since this is a hanging drop experiment, we want to set up the drops as a mirror image, so when we flip the lid back onto the tray, the wells correspond to the drops. So it'll continue doing that for the next, the remainder of the columns. So another feature of the NT8, which is nice, is that it has automatic humidification system. Earlier I was running it with the cover open. Now it's running with the cover shut. That's its normal operating position. And we have humidity set to 75%. And it's going. The humidity allows to prevent sample evaporation and sample consistency throughout the experiment. So the NT8's finishing up the last column of the hanging drop experiment. When it's done, disposes of the tips, plays us a little song, and we're ready to, we have our 96 drops set up on the cover. Okay, so now similar to the mosquito, we're going to use a jig to align the tray and the cover. So I'll take the tray, put it into the jig, I'll take my experiment, flip it over, line it up with the poles, put it down, and again there's our finished hanging drop experiment. Seal it with the brayer, and we already have our barcode set up for the imager, which I'll be talking about next. This is the Formulatrix Rock Imager 1000. It's our automated imaging system. So here I'll go through the different components and the physical layout of our instrument. The imager itself is also a 20-degree temperature-controlled incubator. In the front here is the load port, where the plates get entered into the system. If I carefully open the door, this is the imaging stage where the plate would go, right on there. We also have the visible and the UV microscopes. If we look in here, you can see all the plate hotels. It holds up to 1,000 plates that are the 96 well plate format. And down at the bottom, you see the two hands, which are responsible for moving the plates around the system. Also in the back, with the yellow sticker, we can see the barcode reader. There are two computers that control it. One computer controls the SoftMaker software Rock Imager, which runs the scheduling and also allows you to use the imager as a manually in microscope mode. The second computer runs the program RockMaker, which allows you to design your experiments and look at your images and do much more. We'll get into that in much greater detail later. It has a barcode printer. You print out a unique barcode for each plate. And in addition to these two computers, there is a storage server connected to this that has all the images stored on it and backed up, as well as a web serving server that has RockMaker Web on it, so you can work with your images remotely. So in addition to and complementary to our Rock Imager 1000, we also have a second imager, an RI1, which is an imager that is stored in a 4-degree cold box in the X-ray core. The functionality is essentially the same, except that it does not allow you to do scheduled imaging, as it only holds one plate at a time on the imager. It has visible and UV. What you would do is store your plates in the 4-degree cold box with the barcodes made by RockMaker, and then once per day, or whenever you like, come down, place them on the imager, and image the plate for your So this imager is tied into the same database as the RI1000, so you can do all the functionality that you can with the software as the RI1000. And this provides an excellent complement to a difficult to crystallize protein, where it allows you to have a different temperature at 4 degrees. Rock Imager, which runs the imager and works in conjunction with the software RockMaker. So it does two things. It schedules the auto imaging that's programmed in from RockMaker, and also allows you to image plates manually and get much better images. So we can see here in plates, you can see the full inventory of the plate storage hotels. We can also search for our plates. Plate ID or date, you can see all the plates that are currently in the machine, and we can look at the scheduling, and these are the plates that are scheduled to be imaged over the next couple days. You can see the list here. There's none that are currently queued to be scheduled right now, but this will be the next one that gets imaged at 5 o'clock in the morning. So if we go on to the Imager tab, here you can see all our microscope controls on the right side. Okay, so this is the software that's the user interface for the RI1000 imager. Software is called RockMaker, and this is where you set up your experiments and program the automatic imaging. So let's look at making a new experiment first. So this is our new experiment window here. We'll give it a name. Got today's date, and we're going to do a Hampton Index screen. We have to tell it what plate type it is. In this case, we're going to do a 3-drop sitting drop experiment. And then we're going to program it to tell it to image in visible light at 0 days and hours. And then in this sequence here, and we offset it by 12 hours. So most of the imaging occurs at night when no one's actually using it. We'll then set up a representation of your plate within the computer. So we have to add the well solution. We have all the commercial screens, and we can customize that however you like. Let's get index. And it populates it with the solutions that are in each well. Then we add our protein in. Just grab some protein here. Drop that into the drops. We're able to adjust our drop size here. And basically that's our experimental setup. So now let's look at an experiment that has been run for a while. This experiment here, this is a hanging drop experiment, more aggressive imaging schedule because I know this protein crystallizes faster. So if we look at the results, let's look at 3 days in Canvas. This is the overview of the canvas. So we can quickly look across the canvas, get an overview. You can see the scores in small letters. I'll get to the scores in a second. And then we can look at individual wells that look interesting. Okay, so we can look at each well on the plate, and we can scroll through the wells using the arrow buttons, like so. We can also go back in time and see how these crystals looked at the beginning, 0 hours, the next day. So these grew fairly quickly. And this will give you an indication of what time, how long they take to grow and mature completely. One advantage to that is sometimes crystals grow, they mature, and then they start to degrade. This way, if you miss the perfect time, you can go back and repeat it and know exactly when that is. We can also look at the UV imaging of the crystals. So this is taken in UV. And that's tryptophan, autotryptophan fluorescence. And this is definitely a protein crystal. A couple of tools we can use too. The ruler, useful to tell how big it's going to be when you mount it on the X-ray beam. Also to tell how much it's growing and consistency. And you can compare between drops and conditions of how large the crystals are getting. So that's the Rockmaker software pretty much. You program in what you're going to do ahead of time. It automatically images. Okay, the imaging software is also equipped with the Marco auto scoring algorithm. So Marco is machine recognition of crystallization outcomes. This is an automatic scoring system using AI to determine whether a probability whether you have crystals, precipitant, or clear drops in each one of your drops. This method was published in PLOS ONE, and this is the reference if you'd like to follow up on it. This was done by a consortium of academic groups, folks at Google in their AI program, and private institutions. So basically the way that works in our system is every time your plate gets imaged, the Marco algorithm runs on it and scores it. Here we have the scores from that last plate of percent whether or not there's a crystal in that plate. This can greatly improve your observation of your plates, where if you're pressed for time, you can just look at the plates with high scores. What's also nice is that there's an email server built into the program, so it will email you if it finds what it thinks is a crystal every time it images a plate, which is nice because if you're very busy and you don't have time to look at your plates, or it's a plate that's been in there for a while and all of a sudden there's a crystal, it will tell you. So that's a nice feature. Now we'll use the Rock Imager and the Rock Imager software manually to look at a plate in a little more detail than the automatic imaging gives us. So first thing we're going to do is choose a plate and put it on the imager. So if I go to my plate list, I can pretty much choose any plate, right click, and we'll move the plate up to the imager stage. I have one up there. Let's search for it. And if I hover over it, we can see my plates on the imager. So go up to the imager. Right now, I'll turn on the live image. And we're on well A1 with the lowest zoom at 1. So we can use the well function here to scroll around the plate and look at different wells and identify a particular well we want to look at in a little more detail. So I'm going to choose well A2 here. So first thing I want to do is zoom in a little bit. And then every time we zoom, we want to use the auto exposure function here to get a better image. And we can adjust the Z to stay in focus. So I'm going to be looking at this crystal here. And let's zoom in a little bit more. And we can center. So there's our crystal. Now what I can do is with the Z focus, I can scroll through the crystal, confirm that this is a single crystal, it's not cracked, and there's no defects in it, which we do. And we know it's about 150 microns in each direction from the measuring tool and rock maker. And then if I want, I can zoom all the way in. Adjust our focus and our auto exposure, get it in focus, and then save myself a nice image which is automatically named for a lab meeting or grant proposal or whatever I like. Let me back off to 7 zoom here. That's where I usually like to work. We can also adjust the polarizer. This is useful if you're trying to tell if something is a single crystal or a couple fused together. So here we are at 7 zoom. I'm going to change the autofocus. So now we're going to go into UV imaging to confirm whether this is protein or just a large salt crystal. So we do that by, I work at 7 zoom because that's one of the fixed zoom levels in the UV camera. We switch over to UV. I'll change my objective to 7. And then we'll turn on the illumination and the live image. At this point, we'll look at the crystal. You can always double click to center. And then I want to adjust the exposure and the gain a little bit. The gain's just going to increase both the signal and the noise, but the exposure time will increase how much signal we get. So we can clearly see here that that's a protein crystal due to the auto tryptophan fluorescence. And again, while we're in UV, we can also save this image for our lab meeting presentation, grant proposal, or what have you.